And our next speaker for today is Frederick Rudick and Patrick Kabaudish from Halso Plattner on rock, paper, fibers.
Okay, thank you. So, hello, I'm Frederick Rudick. This is work I did with my advisor Patrick Kabaudish at the Halso Plattner Institute. So, here's a quick preview of rock, paper, fibers. So, to start my audio play, I reshaped the device to a play button. To adjust the volume, for example, make a slider. So with rock, paper, fibers, we are exploring how to improve the physical forms of mobile touch devices by giving them the shape that matches the task at hand. So, and we also demonstrate how to configure multiple widgets at once by adding mechanical constraints. So why are we doing this? So unlike physical controls, touchpads and touch screens have traditionally been flat and featureless. So there's no real physical affordance, so every interaction kind of feels the same. So, but in contrast, tangible objects has wonderful, great physical affordance. So DataTiles is really an interesting mix between these two kind of concepts. So there's still an underlying touchscreen, but Rikimoto added tangible overlays, widgets, that added physical affordance. For example, an embossed groove constrains the user to the touch area forming a dial, and thus affording dialing motion. So, but the vast majority of today's touchscreens are used in mobile devices. So unfortunately, there is not enough space on a mobile device for multiple tangible widgets. So really the goal of rock, paper, fibers is to bring custom-shaped physical controls to mobile touch devices. So the main idea behind rock, paper, fibers is rather than adding something, I take the whole device and reshaping it. And we're doing this for every single interaction. So let me give you a slightly longer walkthrough. So to make the audio player play, I reshaped the device into a play button. As you saw, I have to stroke across the fiber, causing the device to recognize its shape and execute the play button, play command. To adjust the volume, I form a slider. And once again, as you saw, I have to stroke across the slider to register this, and then afterwards I can interact with this widget and control the volume. So here, to get more precision, I can squeeze the slider further, so making it longer. So here, for example, I'm forming a navigation menu, and I can skip to the next track. So I'm forming two rectangular buttons, pauses the audio player. So as you saw in the video, the interactions limits the user to one widget at a time. That is efficient because we're using both hands. So one hand reshapes and the other one interacts. So the contribution of rock, paper, fibers is that we are bringing physical affordance by deforming the device itself, and as to best match the interaction at hand. And we achieve the mobility by serializing this interaction. On the other hand, there are a couple of limitations. So the repeated reconfiguration requires additional time and manual skills, and the range of which is kind of limited. But we deal with some of those limitations later with wedges and clamps. So let's have a look at our hardware prototype. So our prototype consists of a fiber optical bundle which the user can hold and deform. On the other end of the device is just a normal webcam which observes the fiber bundle. And then we have a casing, a 3D printed casing in between, which holds both parts together. So here I'm taking on the viewpoint of the camera, and then looking through the individual fibers. So during touch interaction, the user's finger shadows parts of the fibers, causing them to appear dark to the built-in camera. So we made a range of different prototypes of different sizes. So, for example, at the top we have a more mobile version using a wireless spy cam. So how do we recognize this? So here's a quick guessing game. Is this a slider or a play button? So once again, what do you think, slider or play button? Okay, so let me explain it. So there's actually one big challenge. So whenever the device is reconfigured, it has no way of knowing how fibers are spatially organized. To re-establish this, the user swiped the finger across the device, causing the device to see the fibers turn on and off. So what we count is like the number of touch fibers at a certain time. And basically, plotting this number over time forms a pattern, which you see here. So for the play button, we see a peak at the beginning, and then we see a decrease of number of touch fibers over time. For the slider, we have just a constant small number of touch fibers at all time. So basically, it's just the convolution of the finger and the fiber bundle shape. So the first one was the slider, and the second one was actually the play button. So here's how we process this. So this is the raw camera image you saw before. We do some pre-calibration to find every fiber in the image using half circles. And this is what the camera sees when the user touches the fibers. We just threshold the image and invert it to a binary image, convert it. And then we determine the amount of touch fibers on a per fiber basis. And so this number just represents one position in the resulting pattern. And then we mesh this pattern against a database of labeled widget templates. So we run a quick validation and the recognition rates of kind of so-so, but you can find more details on the paper. So this is the last part I have. And as I showed you earlier, it is kind of a special situation because I'm playing a video game. I don't want to have this extra time to setting up things, and I need to react more quickly. So what I'm using here is like this cross-shaped wedge to create multiple buttons at once, or at the same time. Since I can't use my hands to give different parts of the bundle custom shapes, I'm now using a different mechanism called clamps. And we build a bunch of these kind of clamps. So they're laser cut from 10mm acrylic, and they're using spring armbands from a closest spin. So, and finally, we can use a sieve to create even larger, to create large interaction surfaces that distributes fibers even more, or evenly. And moving the sieve towards the ring spreads out the fibers, enlarges the interaction surface even further. So let me conclude. In summary, with rock paper fibers, we are bringing physical conformance to normal touch devices by making the touch device itself deformable. And we can add some additional expressiveness using these wedges and clamps I showed you. So the vision of the whole thing is that we have a touchpad that we can really reconfigure. So oddly enough, we think of rock paper fibers as a reconfigurable touchpad. So with the community started to bend devices, and we also started to stretch touch devices. But we think this is just the first step in the direction where we're going to create devices that can truly be reshaped in all kinds of ways. For example, taking apart, putting it together, reassembled, and so on. So imagine like a touch-sensitive silly pattern, which we can reconfigure into whatever it takes to best support our task at hand. Here, for example, to play a video game. So, in that sense, we think of rock paper fibers as the first step in this direction to making touch devices truly deformable. So finally, we have an open PhD postdoc position at Hasselblad Institute. So now I'm happy to take questions.